Hello everyone, today I will talk about the elusive concept of gauge invariance. We'll begin with a simple analogy from first year mechanics. Suppose I stand on a desk and drop a ball from some height y. The potential energy of the ball is given by V equals mgy with respect to the ground. I can find the force on the ball, which is the derivative of the potential energy, and we get the following equation of motion. Now, let's say I want to do the same experiment on top of a mountain of some height y0. Well, that would mean that with respect to the ground, my potential will change by some constant V0. Well, once again, we can find the force, and we get the same result in the equation for the equations of motion, since V0 is just a constant and its derivative is 0. So the upshot is that we get the same equations of motion even though our potentials are different. This captures the idea of gauge invariance. Hermann Weyl was the first to introduce the term gauge invariance into English. It comes from the German term Eigenvariance, or invariance under the change of scale. You can think of the quantity V0 as our gauge in this case. We have the freedom of selecting the origin of our coordinate system. This is known as gauge freedom. The type of gauge changes based on the context that you're dealing with, and we see different gauges in the context of electromagnetism, general relativity, and field theory. If a system is invariant under a particular type of gauge transformation, it means that the physics of the system don't change under that transformation, and the equations of motions remain the same. Gauge freedom often allows us to express our equations in a simpler form while still preserving the physics of the system. For example, we can just set V0 to 0 in our example earlier, and it doesn't change the dynamics of the falling ball. We will now move to an example from electromagnetism. This will be a little more advanced and will require some knowledge of vector calculus, since we're dealing with 3 dimensions. We know that the magnetic field can be expressed as the curl of the vector field A. The full form is written as follows, in case you can't remember the formula. It's a derivative of sorts. Now, we can apply a gauge transformation to the vector field A. Our gauge in this case is the gradient of some scalar field lambda, which we add to the potential. The full form is given as well. We pick this to be the gauge because of an important identity from vector calculus that tells us that the curl of a gradient is 0. Now, let's plug this back into our original expression and expand. The part on the right goes to 0 since the curl of a gradient is 0, and we get the same expression back. So, the physics of our system, in this case the magnetic field, remains the same under this family of gauge choices. It tells us that the potential is not unique for a magnetic field, and we can find many different potentials that give us the same magnetic field. We'll conclude with the electric field, which is given as follows, where V is the scalar potential and A is the vector potential. Similarly, we can apply gauge transformation to V, where we subtract the time derivative to the scalar field, lambda from V, and we similarly plug this into the original expression for the electric field, and we expand. The time derivative terms cancels out, and we end up with the same expression. We thus say that the theory describing electromagnetism, Maxwell's equations, that is, are gauge invariant. Gauge invariance is an important feature of the theory, as it tells us that our system conserves charge. This comes from Noether's theorem, and I'm sure you'll learn about this soon. Thanks for listening.